Okay. Never mind. So for number 1, you had this PbNO3 stuff and Ki, right? And so from that, I wanted you to predict it, and I wanted you to give me the states of matter. And if you balanced it, that's even better, right? But something that would have helped you with this is recognizing that you had a transition metal to start with.
Yeah.
And so knowing that that was coming up, you'd have to know its charge so that you know how to crisscross the charges when you recombine things, right? So looking at this, let's just name him first, okay? So you have that Pb with the NO3 little 2, okay? And in order to figure out our charge, we would look at our anion, which was the nitrate, the NO3 part. On your list of polyatomics, we see that it has a what charge? Nitrate.
I got it.
A -1. Good. Good. Okay, so there's 2 of them. So overall, we have a -2 charge. So that means that since we need it to equal 0 or neutral, right, we need to balance it out with a +2 charge. There is only 1 of those, so we would divide it by 1. So overall, he's going to have a +2. Not overall, sorry. The lead is going to have a +2. All right, so that at least tells us that we have lead 2 nitrate, right? So when we go to recombine this, it's good to recognize what type of reaction we have as well, right? What type is that first one?
Double replacement.
It was a double replacement, good. So we would have our Pb, NO3 little 2, Ki. We would switch out the Pb and the K. Okay, so we would end up with KNO3, but we are recombining, so we got to check our charges. So right now, potassium's in group 1. He has a what charge? +1, and nitrate, we just said a second ago, had a -1. So if we crisscross those, we end up with a 1,1. So no subscripts. Okay, and then we're going to have the lead is going to combine with iodine. Lead, we found out earlier, has a +2 charge, and iodine had a -1. So those are going to crisscross to make PbI2. Okay? All right, so states of matter. Since it's a double replacement, what can you tell me the states of matter are of these 2 reactants? You have to be able to mix them together. So think about that. What state of matter does that want? You want aqueous, yep. So double replacements, your reactants are usually aqueous. Okay? And then for the products, how did you figure those out? You had to look at the what? Solubility rules. Good. So when you look at that, we have a alkali metal and a nitrate. Those are always aqueous. Okay, or soluble, good. The PbI2 is we would find iodine on your list. He's under the soluble or aqueous unless it's with silver, lead, or mercury. It is with lead, so that makes this a solid. Good. Okay, did anybody balance it just because it's so much fun?
I balanced it, yeah.
You did? Oh, you did? Good. Okay, so we had 1 lead, 2 nitrates, 1 nitrate. So we would throw a big 2 right here.
Yeah.
Let me do that with a different color, sorry. Big 2 right there. Now I have 2 Ks, so I'm going to throw a big 2 right here. 2 iodines, now you're done. So it was a 1, 2, 2, 1. Okay? Okay. All right, cool. Next, number 2, we had calcium and we had some oxygen. What type of reaction are we looking at for this one? This is a synthesis. Good. So we would combine the 2 together. We know that we have calcium from group 2 is a +2 charge. Oxygen's in group 16, so he has a what charge? -2. We would crisscross those, and you would end up with just to save me some room, sorry. CaO, right?
Yeah.
Okay? Yes. Cow. That is the other kind of cow. All right. Yeah, it looks like chow too. All right. So with this, states of matter. Calcium, what is it? It's going to be a solid. It's a metal. Then we have diatomic oxygen. So what is that?
Yeah.
Good. And then we have CaO. It is a solid. Good job. All right. If you were going to say aqueous, I would still give you the okay because you're doing aqueous when in doubt and it's ionic and whatever. But you really should be thinking about what you've seen in the lab before and kind of look at what your reactants are. If you have a solid and a gas, you aren't just going to magically create some liquid, some aqueous solution. Like that's kind of magic, and we're not doing magic, we're doing chemistry. It looks like magic, but it's science. It is science. All right. So this one should be a solid. It's also kind of like the magnesium that you put in the fire and then it lit up into that bright white light, and what you were left over with is a bunch of ashes in the little evaporating dish. Okay, so which was solid. All right, this one was also very easy to balance. We had a 2 right here, so I threw a 2 in front of this, and then you had to balance that. Okay? All right, so next. The next question had, what is the molar mass of the product from number 2? So as long as you had the right product, this should have been piece of cake. So the molar mass, you would just add together. I feel like my periodic table, sorry. 40.078 plus 15.999. And you would have gotten 56.077. What are the units on this? Grams per mole. Good. Okay. And then finally, for number 4, if you had 5 grams of calcium, and I apologize on my crummy sig figs that I set you up for on this one. How many sig figs am I asking you for? 1. So I would bring my words down to the right. End up with moles on top. So 1 mole is equal to the molar mass of calcium, which I did not give myself enough room. I know, sorry. I'm cheating. There he goes. Okay, there you go. All right, so 40.078. So we would divide it. Hold on 1 second. And then we would get the answer of 0.12 moles, which we would round down to 0.1 for sig figs. So empirical formulas. Empirical formulas are ones that we call simple or simplest.
Yeah.
And it does not mean that it is super simple to calculate. It becomes super simple when you practice doing your homework. But we call them the simplest formula because their subscripts cannot be reduced any further. Okay? So, empirical formulas have the smallest whole number mole ratio of all those different elements that are making that compound. Okay? So in the past, when we have already done the covalent and ionic compounds, remember ionic ones are the ones with the metals. Your ionic ones, they're usually the same as the empirical formula. Because if we had something like from the warm-up today, where I had Ca, and we brought that 2 down in O2, we didn't leave it like that, right? We didn't put Ca2O2. That could be reduced, so we took those away. So this is an example of an ionic one that we reduce automatically because we know to do that. They're in the simplest ratio already. Okay? Yeah, Ca2O2, and I scribbled that out because you don't need them. We already reduced our ionic ones, okay? Okay, for molecular compounds, so if I have something like H2O2, does anybody know what that is?
There's a joke about it.
Hydrogen peroxide. It is hydrogen peroxide. Okay, so that's hydrogen peroxide. Would I ever tell you to reduce that one? No, because if I reduce that and I make it like that, I just made hydroxide. Is hydroxide and hydrogen peroxide the same thing? No, you just changed the identity, and that's not what we're trying to do. All right, so molecular ones, we don't automatically reduce. But today, we're going to be looking at empirical formulas, and if you're asked to give the empirical formula of hydrogen peroxide, that would be when you would reduce those little subscripts. All right. So for molecular compounds, if I ask you for the empirical formula, that'll be when we simplify it down. We reduce all of your subscripts by their common factor. All right. So, what is it? Yeah, I said it right. Okay. All right. So an example that they gave you was this down here. Let's go ahead and practice naming it. It says B2H6. B2H6. So how would you name that right now? Remember, I do not give you a list of prefixes on this next test. Diboron, hexahydride.
Good job.
Okay, so diboron, hexahydride. All right, so just make sure you're still learning those prefixes. Have them memorized by the test. All right, so for this, the molecular formula is something that we would call the true formula. So those are what you've already had to write when I give you prefixes. There will be a calculation way to do it. We'll learn that tomorrow, though. And then empirical formula are the ones that we call simple. Okay, the simple formula. Or meaning the simplified one. Okay, and as you can see, B2H6 got reduced down to BH3. Do you see that? Yep, they divided it both by 2, right? You guys see that? Okay, cool. All right. So that right there is the simplest question that you'll get on the test, where I give you crazy molecular formulas and say, what is the empirical formula? You just reduce them. Okay? All right. Now the math part. So we are going to be taking those percent compositions that you've worked really hard on for the last 2 days. Now we're going to take those percents and work backwards to find the formula. So you could technically take that homework page and look at all the percents that you came up with for homework, and you can now calculate to figure out what those actual formulas are of the things that you took them from. Okay? And it should come out the right way. So the steps that it takes for us to do that, okay, for number 1, you would assume a 100-gram sample. Okay? Now, what I mean by that is that if on your paper I gave you 15.5%, you would take that little percent and you would scribble it out and you would put a G. That is you assuming a 100% or 100-gram sample. Okay. Number 2. Once we have that in grams, so now it's in language that makes sense to us, we're going to convert grams to moles. You guys should know how to do converting grams to moles. But thinking about it and thinking about the way that you set it up, how do we do that quickly without having to set up a whole railroad track? So we would have grams up here, right? Top left, we would have grams. We bring words down to the right. Mole on top, what is this? Gram to mole thing. 1 over your molar mass, right? Your molar mass. So really, all that you're doing, if you have to save space, is you're dividing by your molar mass. Okay? But feel free to still set up the railroad tracks. I still do it. Okay? It's just when you're running out of room, you can just do that. All right. Step number 3. So now that I have everything in moles, you're going to divide all of them by the smallest number. Okay? So I'm going to write a little example off on the side. I don't want you copying it. You don't need to. We will have a big enough example in example 1. Okay? But I want to show you what we're doing technically. All right. So if I have a carbon, hydrogen, and nitrogen, right? And I've done all these steps to where now I have 1.3, 2.6, and 7 moles of everything, right? Looking at that list, we would divide all of them by the smallest, which is what? 1.3, right?
1, 2,
Whatever it is, who cares? All right, but what I want you guys to see is that when we do this one, we end up with one that comes out to be 1. And so what you're doing is now you're comparing all the other things to that 1, right? You're making a ratio. That's all that your subscripts end up being, is a ratio. So like if I'm talking about water, this is a 2-to-1 ratio, right? So this will be a 2-to-1 ratio, and this one will be so on and so forth. That's why we divide by the smallest number. Now, if you choose to forget that, I don't really care. I was just trying to tell you why we do this crazy stuff. Okay? All right. So you're dividing all of them by the smallest. That up there. Okay. The last step, so step 4, is your answers become subscripts. Okay, your answers become subscripts. But put a star there because there is an exception to this. Okay? So just like I showed you before, when we start calculating, after we've divided by the smallest and we get these whole numbers, we put those in as subscripts. However, if I come up with something that says something 0.5 or something 0.3, those are too big of a rounding space to round them to a whole number, all right? 0.5 sits right in the middle. Technically, 0.6 and 0.3, I guess I should have added that, are not really close enough to being whole number, not close enough to being middle, so you gotta mess with them, right? So how can we fix something that ends in 0.5 to be a whole number? What can we multiply it by? Huh? 2. I'm setting up situations that possibly could happen. Okay? And then this one right here, we would say times 3. So back to the little example I just showed you. Push that off to the side. Bringing this back, okay? What we're talking about now is, let's just say we end up with that C has a 1, then we have H2, but now all of a sudden N comes out to be 2.5. Okay? 2.5 is not a subscript. We can't have a whole, it has to be a whole number, right? So we would take that whole thing and basically multiply it by the 2. Oh my gosh. Sorry, guys. Multiply it by 2 to save everything. So now we would have C2, H4, and 5. Okay? You guys see that? Huh? To get rid of the 0.5. That's how you're going to fix it if something ends in a 0.5. But did you notice that we have to do it to everything? You can't just fix that one subscript. Okay?
Should ever be like.
All right, so let's look at example 1. Oops, I wrote that one too far up. Okay. So, for example 1, we have find the empirical formula, and then they give you these percentages, right? So, yep. So we're going to start with step number 1, which is making sure you are assuming 100 grams. So step 1. So that would mean that we have 32.38 grams of sodium. We would have 22.65 grams of sulfur and 44.99 grams of, who's the last one? Sorry, oxygen. All right, so I just took care of step number 1. Step number 2 says to convert everything to moles. So I'm going to show you it with the railroad tracks, but if you would like to just divide it by its molar mass, that's fine. But this way people can kind of follow along with where the numbers come from. So to convert it to moles, I would divide it by its molar mass. So we end up with 22.990 on the bottom. That's just the molar mass of sodium. So coming from the periodic table, 1 mole on top. So if I were to divide those two, I would get 1.408. This is kind of my rule, or something that kind of helps you, because I've seen a lot of mistakes over my years. Okay? Don't round this step. Don't even worry about sig figs in this step. You want to have as many decimal places because you don't want your numbers to be so close, because they will be sometimes. Okay? So you want to take into account little differences. So if you notice, I went all the way to 3 decimal places on this. All right? It happens to be 4 sig figs, but just try not to round that step. Okay? All right. So I did that. Sulfur. I'm going to take sulfur and I'm going to divide it by its molar mass, which... Perfect. Okay. So we get 0.7064. Excuse me. And then the last one, we have oxygen. We're going to divide that one by, have you guys memorized that one yet?
15.99.
Yeah, I was going to say that one you've used a lot lately. Okay? So when we divide that, we end up with 2.812. Okay? So I've just completed step number 2, which is convert everything to moles. Now I'm on step 3. We're going to divide by the smallest.
5.7064.
Yes, good. 0.7064. Good job. 0.7064. 0.7064. All right. So let's start getting those answers. So you can actually... We're not there yet. All right. And some of these, hopefully you're kind of noticing that you could probably do some mental math on actually all of these, right? Like the top one ends up, if you look at it, you have about 14 divided by 7. Do you see that?
Yeah.
Okay. So you can do that, but for now, just type it into your calculator because it has to be whole number ratio or whole numbers anyway, right? So, but
0.208.
I've got 1.993. Sorry. 1.993. Just leave it like a big number for now. We'll talk about the rounding in a second. Okay, the next one, there's our 1. So that's what everyone is getting compared to. And then the last one, you should be getting 3.9807. Okay. So now our final step is those are supposed to be our subscripts. Now we don't ever write things 1.993 as one of our subscripts, right? That would be weird. What is that really, really close to? 2. Good. Okay. This one is 1, so we're good there. And this one is really close to 4, right? So our answer turns out to be Na2SO4, which is, who is that? No, what's the whole compound's name? Sodium sulfate. Good. Good. All right. So that's it. All right. All right. But I do want to walk you through. We're just about out of time, so write fast. Okay. I do want to walk you through how to start example 2 because example 2 has a different start to it. If you look at it, we actually have data. Do you guys see that?
Yeah.
So we have a 10.150 gram sample of a compound. It has only phosphorus and oxygen. Whoa, I just crossed out phosphorus, my bad. And it indicates that phosphorus has this much. So, what can we apply? Well, okay, but what does that give me?
Oh, well, 6.
Okay, let's get our percentages, just like what we've been working on. Can we get percent of phosphorus from this data right here? Yeah. What do we do?
Oh, over, yeah, over 10.
Over the 10.150, and you would multiply it by 100. Just write down the answers for now because I know we're running out of time. 43.67%. Now, can I figure out the percent of oxygen as well?
Yes.
Yes. We can take 100 minus that 43.67. Sorry, I forgot to label this. This is phosphorus. To get me 56.33% oxygen. Now from here, could you just run through the steps and figure out your formula? Yeah. Yeah, you could. Right? Go ahead and do that. We do still have time, so please do not pack up. I still have to give you your homework. So run through this, figure out what is this compound. I will pause the video and kind of keep showing you little steps, but get through it real quick. So this should be where you've gotten things into moles. This is before we divide by the smallest. And the reason I want you guys to do this one before you leave is because this one has the exception in it. So when we divide it by the smallest, by the way, sorry, do we all know what's going on here? So I assumed 100 grams, that's where I changed everything to grams. These are their molar masses, so I'm dividing by their molar masses to get moles. Now I divided it by the smallest to figure out a 1. And this one right here comes out to be, 2.497. There's the awkward one. So we can't have P1O 2.497, right? We would multiply the whole thing by 2 to get P2O5, and that would be the last bit, okay? So I'm about to hand you your homework. You do have to finish at least 3 of the problems, okay? So your homework, this, and you're gonna have to complete 3 of the problems. Are we all clear on that? Any 3, including all the top. The top is piece of cake. You can knock it out in 10 seconds.